Okay, we were asked to do the matrix for a reflection across the x-axis. What's that mean? It means if we have our xy plane and a vector here, that the reflection of that vector across the x-axis maintains the same x-coordinate. The y-coordinate becomes the negative, so it's this. So if this is xy, what's this? This has to be x negative y. Okay, there's your reflection across the x-axis. So, the transformation of xy gives you x negative y. What matrix takes care of that? What matrix accomplishes that? Well, here's the matrix, and you can verify, but you should be able to see what the matrix has to be from this. It's the matrix which multiplies xy and gives you x negative y. Now, the first row has to give you x, starting with the column xy. So this component, the first number, the number you multiply by x, has to be 1, and the number you multiply by y has to be 0 in order to give you x. So your first row is 1, 0. Second row has to have a negative 1 multiplied by y, and there's no x here, so you're going to have to multiply x by 0. You got 0, negative 1. Okay, so here's again a little bigger picture of that transformation. The reflection across the y-axis, well, you would take xy to negative xy. Okay, your x-coordinate would reverse, taking you across the y-axis, giving you a reflection. And same reasoning tells us that this is the matrix that we'd have to use to get this result. In other words, to multiply xy, we have to multiply x by negative 1 and y by 0. It's the only way we're going to get negative x here. And that's what this first row does. And then to get negative xy from the second row of the matrix, we're going to have to multiply x by 0, no x here, and y by 1. It's the only way. So we have 0, 1. Okay, reflection across the origin, well, that actually combines reflection across the x-axis with reflection across the y-axis. And in fact, if we multiply this matrix by this matrix, this is the matrix that we get. So, if we combine a reflection across the x-axis, that takes our vector, let's say, from here down to here, and then combine that with reflection across the y-axis, that's going to take us over to here, and that's going to be reflected through the origin. This vector reflected through the origin. I didn't draw a picture of that. Your book has several good pictures. You should understand that without any problem. And you should verify that then, since first doing this and then doing this gets you here, that if we begin with a vector, multiply by this, and then multiply that by this, we're going to accomplish the reflection. I'm sorry. Yeah, I said it wrong, so I'm going to have to write it out. Okay. Okay, reflection across the x-axis, then a reflection off the y-axis. Yields a reflection through the origin. Your matrix for reflecting across the, well, let's start with the x-axis, is 1, 0, 0, negative 1. For reflection across the y-axis, it's negative 1, 0, 0, 1. If I multiply these together, I get the matrix negative 1, 0, 0, negative 1. You can verify that, which is the matrix that reflects through the origin. So that's kind of important. Okay, if we rotate through angle theta, we get this. I already talked about that in the preceding video. So if theta was, say, 120 degrees, well, you'd have cosine of 120 degrees. A little hard to read, but it's negative sine of 120 degrees. These are hard to read. Sine of 120 degrees, cosine of 120 degrees. In other words, just what I get if I replace all these thetas by 120 degrees. Cosine of 120 degrees is what? Well, it's negative 1/2. You should understand the circular definition of the trigonometric functions and the special angles well enough to derive these if necessary. Okay, the sine of 120 degrees is square root of 3 over 2. So the negative of the sine would be negative square root of 3 over 2. And then you have the value of the sine, which is square root of 3 over 2, and the value of the cosine again, which is negative 1/2. If we multiply this by any vector, we're going to rotate that vector without changing it 120 degrees counterclockwise. So this would be the matrix for rotation through 120 degrees. This is a matrix for expanding by a factor of 3. In other words, whatever our vector is, we keep it in the same direction, we just make it 3 times as long. Well, it should be easy to understand that this matrix does just that. We just multiply the x component by 3, multiply the y component by 3, the vector gets 3 times as long, and its direction doesn't change. Okay? Now, if this is a matrix A and this is a matrix B, what does the vector AB do? Well, what's the first thing, the matrix? What does the matrix AB do to a vector when you apply it? Well, what's the first thing that happens to the vector? It gets multiplied by B. So this transformation expands your vector by a factor of 3, makes it 3 times as long without changing its direction. Then you multiply it by the matrix A, and that rotates at 120 degrees. So we make it 3 times as long, we rotate it 120 degrees. So it expands, then rotates. And I didn't complete my word then. That's so busy to get on to rotation. Okay, BA does what? Well, BA will take your vector, rotate it 120 degrees, then expand it. Now, are those equivalent? Is AB the same as BA? Well, work it out. Think about it. See if that ought to be the case. If tripling the length of the vector and then rotating at 120 degrees has the same effect as rotating at 120 degrees, then tripling it, your answer has to be that the matrix AB has to be equal to the matrix BA. If your answer is then these two products will be different. Well, you can calculate AB, then you can calculate BA and see if they come out the same.